Hello students, welcome to this new video presentation on thermal properties of matter part 2. In part 1, we introduced the topic thermal properties of matter. We also studied about temperature and heat, measurement of temperature, ideal gas equation and absolute temperature, as well as thermal expansion. In continuation of part 1, we are doing this lecture as part 2. In this chapter, we will study about specific heat capacity, calorimeter, and change of state. This is a very important topic and interesting also. So I request you to listen to this lecture very attentively and note down all the important points. We'll start the topic specific heat capacity by conducting some experiments. Take some water in a vessel and start heating it on a burner. Soon you will notice that bubbles begin to move upward. As the temperature is raised, the motion of water particles increases till it becomes turbulent as water starts boiling. What are the factors on which the quantity of heat required to raise the temperature of a substance depend? In order to answer this question, in the first step, heat a given quantity of water to raise the temperature by say about 20 degrees and note the time taken. Again, take same amount of water and raise its temperature by 40 degrees using the same source of heat. Note the time taken by using a stopwatch. You will find it takes about twice the time and therefore double the quantity of heat is required to raise the temperature twice of the same amount of water. In the next step, suppose you take double the amount of water and heat it using the same heating arrangement to raise the temperature by 20 degrees. You will find that the time taken is again twice that required in the first step. In the third and final step, in place of water, if you heat same quantity of some other liquid like oil, say mustard oil or any other oil, and raise its temperature by 20 degrees Celsius. Now you note the time by the same stopwatch. You will find the time taken will be shorter and therefore the quantity of heat required would be less than the required by the same amount of water for the same rise in temperature. These observations show that the quantity of heat required to warm a given substance depends on its mass m, the change in temperature delta T, and the nature of substance. Thus, we will introduce specific heat capacity. Various experiments on heating and cooling of liquids has shown that the quantity of heat required to warm a given substance depends on its mass m, the change in temperature delta T, and the nature of substance. The change in temperature of a substance when a given quantity of heat is absorbed or rejected by it is characterized by a quantity called the specific heat of the substance. Now let us define heat capacity of a substance, which is defined as capital S is equal to delta Q by delta T. So capital S is the heat capacity, delta Q is the quantity of heat supplied, and delta T is the change in temperature. Let it be equation 1. Specific heat capacity. There is another type of heat capacity called specific heat of capacity. It is defined as the amount of heat per unit mass absorbed or given off to change its temperature by 1 unit, and it is represented by letter small s. This is small s. Small s is equal to capital S by small m. Here capital S is the heat capacity which is defined in equation 1. Then substituting the value of capital S, we get small s is equal to 1 by m into delta Q by delta T. Let it be equation 2. Hence, the specific capacity is the property of the substance which determines the change in temperature of the substance when a given quantity of heat is absorbed or given off by it. That is either by heating or cooling processes. It can also be defined as the amount of heat. So it is the amount of heat per unit mass. In the equation 2, if you put m as 1, it becomes the unit amount of heat per unit mass absorbed or given off by the substance to change its temperature by 1 unit. So here in equation 2, if you put m is equal to 1 and delta T is equal to 1, then specific heat per unit mass is defined, is the quantity of heat. It depends on the nature of the substance and its temperature. The SI unit of specific heat capacity is joules per kg per Kelvin. The third type specific heat is the molar specific heat. If the amount of substance is specified in terms of moles instead of mass m in kg, we can define heat capacity per mole of the substance by capital C is equal to S by mu. That is, here capital C is the symbol of molar specific heat equals S. Capital S is the heat capacity and mu is the moles. That is equal to 1 over mu into delta Q by delta T. Let it be equation 3. So we have defined capital S, small s and capital C in equations 1, 2 and 3. The specific heat capacity of gases. It is observed that the specific heat capacity of gases varies with pressure and volume. Hence, there are two types of specific heat capacity of gases. For the specific heat capacity of gases, additional conditions are needed to define capital C, that is molar specific heat. In this case, heat transfer can be achieved by keeping either pressure or volume constant. If the gas is under constant pressure during the heat transfer, then it is called the molar specific heat capacity at constant pressure, and it is denoted by the letter capital C subscript P. Here the subscript P represents constant pressure. Similarly, if the volume of the gas is maintained constant during the heat transfer, then the corresponding molar specific heat capacity is called molar specific heat capacity at constant volume, and it is denoted by the letter capital C subscript V. Now we will study about the specific heat capacity of some substances at room temperature and atmospheric pressure, and we will compare different substances. The table 1 shows the specific heat capacity of some substances at atmospheric pressure and ordinary temperature. We may note that has the highest Water has the highest specific heat capacity of 4186 joules per kg per Kelvin. For this reason, water is also used as a coolant in automobile radiators as well as a heater in hot water bags. Owing to its highest specific heat capacity, water warms up more slowly than land during summer, and consequently wind from sea has cooling effect. Now you will know why in desert areas the earth surface warms up quickly during the cools quickly at night. We will study about this cooling effect land and sea in section 11.8. Table 2 shows the molar specific heat capacity of some of the gases. Here also you please see the column number 2 gives the molar specific heat at constant pressure in joules per mole per Kelvin. So at constant pressure, take for example a gas helium. It has got Cp of 20.8. Whereas if you keep the volume as a constant, then helium's Cv, that is molar specific heat, is 12.5. Please note the difference. If you keep the pressure constant, then Cp is higher than Cv. Please note down all these points and go through all the gases: helium, hydrogen, nitrogen, oxygen and carbon dioxide. Now we will study about calorimetry. A system is said to be isolated if no exchange or transfer of heat occurs between the system and its surroundings. When different parts of an isolated system are at different temperature, a quantity of heat transfers from the part at higher temperature to the part at lower temperature takes place. The heat lost by the part at higher temperature is equal to the heat gained by the part at lower temperature. Calorimetry means measurement of heat. When a body at higher temperature is brought in contact with another body at lower temperature, the heat lost by the hot body is equal to the heat gained by the colder body, provided no heat is allowed to escape to the surroundings. A device in which heat measurement can be done is called calorimeter. The calorimeter consists of a metallic vessel and a stirrer of same material like copper or aluminium. Please see the figure on the right hand side. So it has got a vessel and a stirrer. This is stirrer. The vessel is kept inside a wooden jacket. The vessel is kept under a wooden jacket which contains heat insulating material like glass wool, etc. So that means we have to prevent the escaping of heat to the surrounding, so that whatever happens, it happens inside the vessel only. The outer jacket acts as a heat shield and reduces the heat loss from the inner vessel. There is an opening in the outer jacket through which a mercury thermometer is inserted into the calorimeter. Please see the figure on the right hand side. This is T2 is a thermometer, and this is stirrer, and this is a vessel, wooden jacket for insulation, calorimeter. The principle of heat gained equals heat lost is used to calculate the specific heat capacity of a substance. The worked example given in the next slide explains the detailed calculation. Worked example. We will take up question number 3. A sphere of 0.047 kg aluminium is placed for sufficient time in a vessel containing boiling water, so that the sphere is at 100 degrees centigrade. It is then immediately transferred to 0.14 kg copper calorimeter containing 0.25 kg water at 20 degrees centigrade. The temperature of water rises and attains a steady state at 23 degrees Celsius. Calculate the specific heat capacity of aluminium. Please read the question once again and try to understand the question. Here we are required to calculate the specific heat capacity of the aluminium. Answer. It is given items are mass of the aluminium sphere is equal to M1, that is equal to 0.047 kg. Then initial temperature of aluminium sphere is 100 degrees Celsius. Then final temperature is 23 degrees Celsius. Change in temperature, therefore delta T is equal to 100 minus 23, that is equal to 77 degrees Celsius. Let the specific heat capacity of aluminium be S of S subscript Al, that is specific heat of aluminium is small s Al. The amount of heat lost by aluminium sphere is mass into specific heat into change in temperature. Therefore, it is given by the formula M1 into S aluminium into delta T. That is equal to 0.047 kg into S aluminium into 77 degrees. We have to calculate the value of S aluminium. Now the mass of water is M2. Let the mass of water be M2 and it is given as 0.25 kg. So mass of calorimeter M3 is 0.14 kg. This is also given. Initial temperature of water and calorimeter is 20 degrees centigrade Celsius, 20 degrees Celsius. It is also given. So final temperature of mixture is, it is also mentioned in the question, 23 degrees Celsius. Therefore, change in temperature is delta T2, that is equal to 23 minus 20 degrees. So initial stage it came down from 100 to 23 and later on it came down from 23 to 20. That is equal to change in temperature is 3 degrees Celsius. Therefore, specific heat capacity of water. So now we have to calculate specific heat capacity of water. That is equal to 4.18 into 10 cube joules per kg per Kelvin. This is also we have to find out from the table. Specific heat capacity of a copper calorimeter. So that also we have to note that it is given 0.386 into 10 to the power of 3 joules per kg per Kelvin. This is also given in the table shown in the previous table. The amount of heat gained by water and calorimeter is M2, that is the mass of water into change in temperature with water delta T2 plus M3 is the mass of calorimeter into specific heat of copper, that is copper delta T2 change in temperature. Therefore, taking M2 SW plus M3 S delta T2 common, we get the above equation, previous equation becomes N2 SW plus M3 SCU into delta T2. Therefore, substituting the values, M2 is 0.25 kgs and SW is 4.18 into 10 to the power of 3 joules per kg per Kelvin plus M3 is 0.14 kg into specific heat of copper is 0.386 into 10 to the power of 3 joules per kg per Kelvin into the change in temperature is 23 degrees Celsius minus 20 degrees Celsius. In the steady state, heat lost by aluminium sphere equals heat gained by water plus heat gained by calorimeter. So therefore heat lost is 0. This is from this equation, equation 1, 0.047 kg into S aluminium, which we are required to find out, into 77 equals heat gained is equal to, this is given by this equation, previous equation number 2. So substituting and simplifying, we get the value of specific heat of aluminium as 0.911 joules per kg per Kelvin, kilojoules per kg per Kelvin. Kilojoules, this you please note, simplifying you will get it. Next topic is change of state. Matter normally exists in 3 states, that is solid, liquid and gas. A transition from one of these states to another state is called change of state. So if the matter changes from solid to liquid and liquid to gas, then change of state occurs. Two common changes of states are solid to liquid and liquid to gas and vice versa. These changes can occur when the change of heat takes place between substance and its surroundings. To study the change of state on heating or cooling, we can perform some activity. That activity is shown in the next slide. Before we take up that experiment, we will define some physical quantities and physical changes. Melting. The change of state from solid to liquid is called melting, and from liquid to solid is called fusion. So, if the substance changes becomes from solid to liquid, it is called melting, and from liquid to solid, it is called fusion. Melting point. The temperature at which the solid and liquid states of substance are thermal equilibrium or in the thermal equilibrium with each other is called its melting point. I will read it once again. The temperature at which the solid and liquid states of substance are in thermal equilibrium with each other is called its melting point. Melting point is a characteristics of a substance and changes with change in pressure. The melting point of a substance at standard atmospheric pressure is called normal melting point. Please note, at standard atmospheric pressure, the melting point is called normal melting point. If you say normal melting point means it is measured at standard ATM, atmospheric pressure. Fusion. Then the next term is fusion. The change of state from liquid to solid is called fusion. Vaporization. The change of state from liquid to vapor or from liquid to gas is called vaporization. It is observed that temperature remains constant while the entire amount of liquid is converted into vapor. Boiling point. The temperature at which the liquid and vapor states of a substance coexist is called the boiling point. The boiling point of a substance at standard atmospheric pressure is called normal boiling point. Please note, the boiling point at standard atmospheric pressure is called normal boiling point. Sublimation. The process of change from solid state to vapor state without passing through liquid state is called sublimation. That means if a solid state is directly changes to vapor, then it is called sublimation. The melting process of ice can be performed using an experimental setup shown in figure B, and the process itself can be represented graphically as shown in figure A. For doing this activity, you can set up the experimental setup as shown in the figure. Take a slab of ice, take a metallic wire and fix two blocks each of 5 kgs as shown in the figure. These are the two blocks of 5 kg each. Say at its ends, put the wire over the slab as shown in the figure on the right hand side. You will observe that the wire passes through the ice slab. This happens due to the fact that just below the wire, ice melts at lower temperature due to increase in pressure. When the wire has passed, water above the wire freezes again. Thus, the wire passes through the slab and slab does not split. This phenomenon of refreezing is called rigellation. Skating is possible on snow due to the formation of water under the skates. Water is formed due to increase of pressure and it acts as a lubricant. After the whole of ice gets converted into water and as we continue further heating, we shall see that the temperature begins to rise as shown in figure A. The temperature keeps on rising till it reaches nearly 100 degrees centigrade. You see, this is temperature 100 degrees centigrade and this is the 0 degrees temperature. The heat supplied is now being utilized to change water from liquid state to vapor or gaseous state. The change of state from liquid to vapor or gas is called vaporization. It is observed that the temperature remains constant until the entire amount of liquid is converted into vapor. So it remains at temperature 100 degrees centigrade till the entire liquid is converted into vapor. That is, both the liquid and vapor states of the substance coexist in thermal equilibrium. So this is the state of thermal equilibrium during the change of state from liquid to vapor. The temperature at which the liquid and the vapor states of the substance coexist is called the boiling point. Phase diagrams and triple point. A graph between temperature capital T and pressure capital P of substance is called the phase diagram or P-T diagram. These graphs in respect of water and carbon dioxide are shown on the screen as figure A and B. Consider the graph in respect of A. Here, the graph shows three regions: the solid region, the liquid region, and the vapor regions separated by the curves BO, AO, and OC. The curve BO is called the sublimation curve, and the curve AO is called the fusion curve, and OC is called the vaporization curve. Any point on BO shows the existence of both solid and vapor. Similarly, the point on the curve AO shows the coexistence of solid and liquid states, and the point on OC shows the coexistence of liquid and vapor state. The point at which BO, AO, and OC, that is the sublimation curve, the fusion curve, and vaporization curve meet, is called the triple point of a substance. For example, the triple point of water is represented by temperature 273.16 and pressure of 6.11 into 10 to the power of minus 3 pascals. This is the point. And similar in the case of carbon dioxide, the region solid state is large and vapor state is also large, whereas liquid state is very narrow. The difference you can make out yourself. Latent heat. We have seen in the previous section that certain amount of heat energy is transferred between a substance and its surroundings when it undergoes a change of state. The amount of heat per unit mass transferred during the change of state of the substance is called the latent heat of substance for the process. It is represented by letter capital L. Hence, latent heat capital L is the amount of heat per unit mass transferred during the change of state of the substance. For example, if heat is added to a given quantity of ice at minus 10 degrees Celsius, the temperature of ice increases until it reaches its melting point 0 degrees Celsius. That is, from it consumes quantity of heat for raising the temperature from minus 10 degrees Celsius to 0 degrees Celsius. At this temperature, that is at 0 degrees Celsius, the addition of more heat does not increase the temperature but causes the ice to melt or change its state. Once the entire ice melts, adding more heat will cause the temperature of water to increase. A similar situation occurs during liquid-gas change. So in the previous example, we had seen the change of state from solid to liquid. Similar situation occurs during a liquid liquid to gas change of state at the boiling point. Adding more heat to boiling water causes vaporization without increase in temperature. The heat required during a change of state depends on the heat of transformation and the mass of the substance undergoing a change of state. Thus, if a mass m of a substance undergoes a change from one state to other state, then the quantity of heat required is given by Q is equal to small m into capital L, or L is equal to Q by m. Here Q is the quantity of heat and m is the mass. Let it be equation 1. Here L is known as the latent heat and is a characteristics of the substance. The SI unit of latent heat is joules per kg. The value of L also depends on the pressure. Its value is usually quoted at standard atmospheric pressure. So latent heat of a substance is generally quoted at standard atmospheric pressure. The latent heat for a solid liquid state change is called the latent heat of fusion. That is, from when a substance changes its state from solid to liquid, its latent heat is called heat of fusion, and that of liquid to gas state is called latent heat of vaporization, represented by the letter capital L subscript V. These are often referred to as heat of fusion and heat of vaporization. In order to explain the change of state, we have to study the temperature versus heat graph. This graph is shown in respect of water at 1 atmospheric pressure. This is not to scale, but still it is representative in nature. Please note that when the heat is added or removed during a change of state, the temperature remains constant. Please see at the melting point, that is 0 degrees Celsius, the temperature remains constant, whereas the heat increases. Similarly, at the boiling point, that is a change of state from liquid state to gaseous state, the temperature remains constant at 100 degrees Celsius and it is flat. Also note that the slopes of the phase lines are not all the same, which indicates that the specific heats of various states are not equal. Let us study about the temperature and change of state and latent heats for various substances at 1 atmospheric pressure. Table number 3 shows the melting point, boiling points and latent heats at 1 atmosphere pressure. The substances are given in column number 1. For example, take for ethanol. Ethanol, the melting point is minus 114 degrees Celsius, whereas latent heat of fusion is 1.0 into 10 to the power of 5 joules per kg. This is the latent heat of fusion. The boiling point of ethanol is 78 degrees centigrade and its latent heat of vaporization is 8.5 into 10 to the power of 5 joules per kg. Similarly, it is given these values are given for other substances like gold, lead, mercury, nitrogen and oxygen. So finally for water, the melting point is 0 degrees Celsius. Its latent heat of fusion is 10 to the power of 3.33 into 10 to the power of 5 joules per kg. The boiling point of water is 100 degrees Celsius and its latent heat of vaporization is 22.6 into 10 to the power of 5 joules per kg. Now we will solve some worked examples. Before we conclude this part, question number 4. When 0.15 kg of ice at 0 degrees is mixed with 0.3 kg of water at 50 degrees Celsius in a container, the resulting temperature is 6.7 degrees Celsius. Calculate the heat of fusion of ice. It is given that specific heat of water is 4.186 joules per kg per Kelvin. So please read the question and note down the given quantities. Answer. Heat lost by water is given by mass into specific heat into change in temperature. Therefore, it is 0.3 kg into 4186 joules per kg per Kelvin into 50.0 degrees Celsius minus 6.7 degrees Celsius. 6.7 degrees Celsius. Therefore, simplifying, we get heat lost by the water as 54,376.14 joules. So, heat required to melt the ice. So, it is given by mass into latent heat of fusion. So, that is equal to, we are required to calculate, the question asked it, we have to find out the value of LF. Therefore, M2, mass of ice is given as 0.15 kg. So, M2 is 0.15 kg into LF. LF we have to determine. Therefore, heat required to raise the temperature of ice water to final temperature is equal to M1 into SW into theta F, that is final temperature minus initial temperature of ice. This subscript I is for ice. Therefore, it is M1 is 0.15 into 4186 joules per kg per Kelvin into 6.7 minus 0 degrees Celsius. Therefore, multiplying and simplifying, we get the value as 4206.93 joules. Therefore, equating heat lost is equal to heat gained. So, the heat lost by water is 54,376.14 joules, that is equal to 0.15 kg into LF plus the heat required to raise the temperature of ice water is 4206.93 joules. So finding the value of L from the above equation, we get LF is equal to 3.34 into 10 to the power of 5 joules per kg. Please repeat the question, write down and work out yourself. Next question. Calculate the heat required to convert to convert 3 kg of ice at minus 12 degrees Celsius kept in a calorimeter to steam. That is converting the 3 kg of ice to steam at 100 degrees centigrade at atmospheric pressure. Given specific heat capacity of ice 2100 joules per kg per Kelvin. The specific heat capacity of water is 4186 joules per kg per Kelvin. Latent heat of fusion of ice equals 3.35 into 10 to the power of 5 joules per kg, and latent heat of steam is equal to 2.256 into 10 to the power of 6 joules per kg. Please note down the given values separately step by step. So I will answer the question. Answer: given mass of ice is given as small m is equal to 3 kg. Specific heat of ice, S subscript ice is equal to 2100 joules per kg per Kelvin, and specific heat capacity of water is S subscript water is equal to 4186 joules per kg per Kelvin. Latent heat of fusion of ice is LF ice, that is latent heat of fusion of ice is equal to 3.35 into 10 to the power of 5 joules per kg. Latent heat of steam is L steam equals 2.256 into 10 to the power of 6 kg per kg. So pause the video and note down all these steps. So let Q be the heat required to convert 3 kg of ice at minus 12 degrees centigrade to steam at 100 degrees Celsius. That is minus 12 degrees Celsius to 100 degrees Celsius. So Q1 equal to heat to convert ice at minus 12 to ice at 0. Please note down the temperature difference. Minus 12 degrees ice to 0 degrees ice is m into S ice into delta T1. Substituting the values, we get Q1 as 75,600 joules. Q2 is equal to heat required to melt ice 0 degrees Celsius to water at 0 degrees. That is constant temperature 0 degrees 0 degrees. Therefore, it is given by m into LF, latent heat of fusion of ice. So that is the values are given, and we can find out 100 100,500,000 joules. Therefore, Q3, the heat required to convert water at 0 degrees centigrade to water at 100 degrees centigrade Celsius, that is equal to m into SW into delta T2. So substituting the values, we get 3 into 4186 into 100, that is equal to 1255800 joules. And there is another heat required to convert water at 100 degrees to steam at 100 degrees. Here the temperature remains constant. Therefore, Q4 is equal to m into L of steam, that is latent heat of steam. That is, the substituting the values, we get 6768,000 joules. Hence, the total quantity of heat required to convert 3 kg of ice is given by Q is equal to Q1 plus Q2 plus Q3 plus Q4. These values we have calculated separately. So therefore, adding, we get the result as 9.1 into 10 to the power of 6 joules. Please pause and note down step by step. With this, we come to the conclusion of part 2. Next chapter, we will take up part 3, in which we will study about heat transfer, Newton's law of cooling, as well as we will answer some questions. Till then, Goodbye.